Hi, everyone. This is Elton from Fidelity. I'm the Director of Quantum Research at Fidelity Center for Applied Technology. And today I'm going to talk about explainable AI with quantum. OK, that's the slide. What's FCAT? FCAT stands for Fidelity Center for Applied Technology. It's a catalyst for breakthrough ideas driven to help build a successful future for Fidelity and its customers. So we identify and track important trends in society and technology. We test and validate emerging tech, such as blockchain, AR, VR, metaverse, quantum, and future computing. We develop and bring new capabilities and products to scale. So in FCAT, we are experimenting with quantum and future computing now to help ensure that we are well positioned for the future. What is explainable AI? And just to set the ground up. Explainable AI, there are many different ways to call it. You can say it's interpretable AI, explainable machine learning. This refers to AI systems over which it's possible for humans to retain intellectual oversight. And what does that mean? So for example, if you look at an example on the right, in the first picture, this is a very simple feed-forward neural network. This is what we typically understand as AI. For example, what's happening in ChatGPT and all of generative AI is basically those kind of models. On the right, that is an example of explainable AI, and this is what we are doing. So the fundamental difference there is that why do we, you may wonder, like, hey, the AI systems that we have, they work very well. So why do we need explainable AI? So this is often desired or even mandatory in industries with heavy regulation. For example, financial services, healthcare, and so on. And also, explainable AI adds a transparency to AI models and help bring trust to customers, product owners, and regulators. So what we are doing with explainable AI, so here I'm very happy to describe to you our work, which is called Explainable AI with Expressive Boolean Formulas. And this is a collaboration of FCAT, the AI Center of Excellence within Fidelity, and the AWS Quantum Solution Lab. So I would just want to give credit to all of my co-authors. And actually, I think Grant Sultan is probably in the audience here. I'm sorry, the lights are shiny. Yeah, and so I'm also happy to say that our work has just been, as of 2 weeks ago, it has been recently published at Machine Learning and Knowledge Extraction, special issue on advances in explainable artificial intelligence. So this work has been peer-reviewed already. And also, in terms of potential use cases, we think that this is widely applicable to a lot of different industries. For example, credit application. Suppose you want to apply for credit, and typically, for example, if you apply for a credit card, if you get rejected, the bank will probably send you a letter explaining, hey, why you are being rejected. Maybe your history is too low. Maybe you have too many accounts. And in that case, we can't have a black box model that tries to make the decision. In marketing campaign, suppose you are a product owner and you launch a product to your customers, and you're collecting your data, and in a few weeks, you see that there's a group of customers who seems to sign up for your product, and then there are other people who didn't. You may want to understand, what's going on, what is differentiating between these two groups. In fraud detection, we want to design transparent systems that can tell you, what are the likely fraud cases, so that we can design better, engineering practice for that, training prediction, and so on. So there's a lot of different use cases. So a high-level idea of what we are doing is that, so here we call this a classification problem, because like you always have some data that is maybe a churn maybe some other data that is not a churn, or segregation between customers. So this is fundamentally a classification problem, so which is in the regime of supervised machine learning. So we have some data, we have some labels. So ultimately, the goal is that there's a solver that can do this classification and result in a model that is easily interpretable. So here, we are constructing such a model based on a simple set of rules. For example, and, or, at least, at most, based on the features of the data set. And we want a model with a minimal number of features and maximal accuracy. So next, I'll give you a very simple example of how such a model works. And just for clarification, this is for illustrative purpose and not a medical advice. So on the left, you can see that this is suppose I'm a patient going to see a doctor, and these are these are a list of symptoms that I have, and I want to understand whether I have flu or not. On the right, this is a simple explainable model that the doctor uses to diagnose flu. So so the plus are the ones that I have symptom, and if there's not a plus, then it means that I don't have that symptom. So for example, if we first look at the bottom part of the rule, we'll say that, hey, it seems that this patient has fever, has sore throat. It doesn't have a runny nose, but that's fine, because our condition says that, hey, at least two of the conditions are satisfied. Then this is a yes. So okay, so we have the first condition checked, and then this patient also has body ache, so it checks the second condition. And now, because if we look at the root node, that's an and, because all the conditions below are satisfied, so it means that the and operator is also satisfied. So based on this, the doctor can say that yes, this patient has flu. So how are the rules constructed? You may wonder. So suppose this is this is a base case, and there are many different things that one can do to construct such rules and find better rules. So the idea that I'm presenting, this is based on simulated annealing. So for example, you can imagine like playing with Lego pieces. You can add a Lego piece on top of that. You can remove a Lego piece. So it's very similar idea. So here you can remove a node. You can remove a literal from your model. You can add a literal. You can remove an operator. So here you can see that we remove the operator and just collapse this model from 2 levels down to 1 level. Or you can insert a new operator. So this becomes 3 layers. So far this is all nice and good, but there's nothing quantum here yet. This is all very classical algorithms. So where does quantum come in here? So remember, what we did just now, is really all like one piece at a time. This can be a little bit expensive. So what if we can optimize things on a global level? So here, saying like suppose the operation that I want to do is like to replace this operator of choose 2 with an or, and optimize everything under. Of course, you can still play in like the Lego game and add different pieces on top of that. But there's another way that you can do it, which is to use a quantum computer or a quantum-inspired device. So here, I won't talk about this in detail, but you can formulate this sub-problem of optimizing like all the literals under this operator as a Kubo problem or as an integer linear programming problem. So you can use your favorite solvers. For integer linear programming, there's a lot of open source and commercial optimization solvers. You can use your favorite Kubo solvers out there. There's a lot. There's a lot of them. So I'm not going to go to too much detail that everyone knows how to do that. So good. now I'm going to talk about a more sort of realistic use case. So this is a public data set that I take from the the UCI machine learning repository, and you can see like the relevant details and acknowledgement is done at the corner. So this is a marketing campaign from a European bank for a term deposit subscription. So what happens is that they have a marketing campaign, and they're calling their clients and trying to see whether any one of them wants to sign up for their term deposit subscription. So here, there are about 41,000 clients with 21 features describing the personal information and some socioeconomic indices. So this data is collected over the 2 years immediately, I think in the middle of the financial crisis, maybe 10 years ago. So if we look at the data, there's all the customer-related data. For example, age, job, marital status, education, and so on. And then there are some campaign-related data. For example, like how are the customers being contacted, whether it's cellular or telephone. And then there are some macroeconomic data. The last one, the label, which yes says that the client subscribed to the term deposit, and no means that the customer did not subscribe. So very, very, very easy to understand data set. So so the goal here is to find a simple rule based on only a few features that can estimate whether a customer is likely to subscribe or not with very high accuracy. And here the goal is not to achieve an accuracy of like 99%. If you want to do that, use your favorite black box models such as random forest, XGBoost, or anything else. So here is to come up with an explanation so that we can understand why some clients are making this decision and why some others are not doing that. So we put this to the model, and this is what the model come up with. So here there are parameters that one can set. So here I just set it to be an extremely simple model, with 4 boxes. You can go a little bit more complex if you want. So let me try to explain this a little bit, because not everyone is familiar with this data set. So what does this tell me? This tells me that, so the first one is the duration of the call in minutes. So this tells me that a client is more likely to subscribe if the call lasts for more than 8 minutes. It seems to make sense. If you can keep the call a little bit longer, it means that your client will be a little bit more engaged. The second one is, this is like a social economic data. This is the 3 months European interest rate, which I'm not going to explain. I don't really know too much about that. And the last one says that if the client is between the age of 65 to 74, then they're more likely to subscribe to this product. So I'm not the product owner here, so I don't really know what's going on. But maybe they know that hey, maybe they need to design their product to better attract the younger population and so on. So okay, so that's a rule, and with the accuracy, this can explain about 83% of the data, which is not bad. We're not aiming for like a 99% accuracy. The whole goal is to make sure that whether there's something that we can use to explain why we're having different customer behaviors. So what's the takeaway here? So the takeaway is that so we take a very practical business problem and help solving it by designing an explainable AI framework based on these Boolean formulas, and or at least at most. Okay. And we show that the hardware acceleration can be used and potentially leading to a speed up. And remember, if you are just doing this simulated annealing process, you are doing these Lego pieces. You are inserting one piece, removing one piece. If you are using a like a commercial solver, like a QUBO or ILP solver, if you have a quantum or quantum-inspired backend, this can do that in one go. So that can potentially lead to speed up and also help you, get rid of like local minimas and so on. So quantum-inspired hardware, software providers, of course, they still have to show that they can solve these optimization problems at scale, because we're doing many iterations of such that, and sometimes the search space can be a few hundred. So that's not a very small problem. And we believe there's a lot of interesting use cases here. So lastly, I just invite you to connect with our organization through this QR code. And thanks so much. I think I may be able to some questions.
We can open the floor for questions if there are any.
Thank you for the talk. My question is, so when you said how we get quantum into this system, and the answer was that we use optimizers like QUBO or other similar ones, is that the core bit how quantum get into that system, or is there another way how quantum computing is attached to this approach to make the AI more explainable?
Yeah, that's right. For now, we think that the place where quantum can come in is can do this, do like a global sort of a regional, like we call it like a non-local moves within a node. Like if you can solve this to optimal, then this will help with the construction of the model. But of course, there may be other ways that quantum can help. If you can think of other ways, feel free to get in touch with us. Yeah.